Hi guys, in the previous video we discussed about transforming an inexact differential equation to an exact differential equation by multiplying the inexact differential equation by a suitable function known as the integrating factor. And we showed an example as to how we can go about this. Now we don't just randomly guess what the integrating factors are. There are laid down rules for obtaining the integrating factors. Now let's consider an inexact differential equation p dx plus q dy is equal to 0. So this is an inexact differential equation. Now, in order to convert this inexact differential equation to an exact differential equation, we'll multiply this differential equation by an integrating factor. Let's call our integrating factor f. So we can show this mathematically by saying f multiplied by p dx plus q dy is equal to 0. And this is the exact differential equation, or we can simplify it further to give us fp dx plus fq dy to be equal to 0. So this is our exact differential equation because we've multiplied the original equation, which was p dx plus q dy, by our integrating factor f to give us this new equation fp dx plus fq dy is equal to 0. So we can compare this with our exact differential equation, the general form of our exact differential equation, m dx plus n dy, which is equal to 0. So from this comparison, we can see that m is equal to fp and n is equal to fq. Now to check for exactness of this differential equation, we apply the condition for exactness of a differential equation, which is the partial derivative of m with respect to y must be equal to the partial derivative of n with respect to x. So by doing this, we are trying to show that the m dy should be equal to the n dx. Then invariably, we are saying that d dy of fp is equal to d dx of fq, because m is equal to fp and n is equal to fq from the comparison we made earlier. Now we can apply the product rule to this. To apply the product rule, we now have the fyp plus fpy must be equal to fxq plus fqx. Now you might be wondering what the subscripts x and y mean. So fy is the same thing as the partial derivative of f with respect to y. Just a simpler way to write it. Fx is the partial derivative of f with respect to x. Py is the partial derivative of p with respect to y, and our qx is the partial derivative of q with respect to x. So with that being said, we just wrote it in this format just to reduce the ambiguity of the solution of the expression, as the case may be. So if we are examining this solution, we need to solve for x. But if we want to solve this particular equation for f, it's going to be pretty complicated to solve, because now we have partial derivatives of f in terms of y, or with respect to y, and we also have partial derivative of f with respect to x. Likewise, we have partial derivative of p with respect to y, and partial derivative of q with respect to x. So this is going to be very tedious to solve. It's not impossible, but it's very complicated. So in order to reduce the ambiguity, we try to look for an integrating factor in only one variable. That is, f will either depend purely on x alone, or it depends purely on y alone, and not a mixture of the both of them. So we are going to be considering two cases. The first case we are going to be considering is a case where f, which is our integrating factor, is solely a function in x. And the second case is when f is solely a function in y. So we're going to be taking a look at these two case studies to simplify our solutions, rather than taking f as a function of two variables, that is x and y. So let's take a look at the first case study. So in the first case, let's call that case 1. Now, if we let f be a function in x only, that is, f is a function in x as written here, it means fy, f subscript y, sorry, that is the partial derivative of f with respect to y, is equal to 0, and fx, that is the partial derivative of f with respect to x, is the same thing as df dx, that is, sorry, let me write that. This is the complete derivative, since f depends only on x. Now, let's go back to our equation that we obtained earlier from the product rule in testing for the exactness. So fyp plus fpy is equal to fxq plus fqx from the results we obtained earlier. That is the result obtained from here. Call that equation asterisk. So you can easily refer to this from equation, sorry, asterisk, we have this. So let's substitute the values that we know. So we know that fy is 0. So this expression automatically becomes 0. So we now have fpy to be equal to q df dx plus fqx. Therefore, we can divide through by fq. So we can divide through by fq. On doing that, we have 1 over fq multiplied by fpy to be equal to q divided by fq df dx plus f divided by fq multiplied by the partial derivative of q with respect to x. So in simplification, we now have py, which is the partial derivative of p with respect to y. We could call it p subscript y, must be equal to 1 over f df dx plus 1 over q multiplied by, we could also write q subscript x divided by q. So that sorts it out. We can collect like terms here, saying 1 over f df dx will now equal p subscript y divided by q minus q subscript x divided by q, which can be further simplified as 1 over q into brackets p subscript y minus q subscript x. So now we have that 1 over f df dx will be equal to 1 over q p subscript y minus q subscript x. So we now have that 1 over f df dx is equal to 1 over q, the partial derivative of p with respect to y, minus the partial derivative of q with respect to x. And this can be rewritten as 1 over f df dx to be equal to r, where r is equal to 1 over q dp dy minus the q dx. Now, we recall that the original equation was p dx plus q dy equal to 0. So if this original equation is in such a way that on evaluating r, that is 1 over q the p dy minus the q dx, we get a function of x only, then let's call this equation 1. Then equation 1 has an integrating factor of f, which is equal to a function in x only, as earlier said. So it means when we assume f to be a function in x only, we arrive at an equation 1 over f df dx is equal to r, and r is equal to 1 over q multiplied by the partial derivative of p with respect to y minus the partial derivative of q with respect to x. So in evaluating r, if we get a function in x only, mathematically, what we now have is this. We have that 1 over f df dx must be equal to r, which is a function in x only. And since we said f is a function in x only, we can easily evaluate this result by using our separation of variables method. Remember, we've talked about this before. So by separation of variables, Separation of variables, we have df all over f must be equal to rx dx. So you can go ahead to integrate both sides of the equation. So by integrating both sides, we now have that df, the integral of df all over f must be equal to the integral of rx with respect to x. Recall, r is only given as a function of x if after evaluating 1 over q the p dy minus the q dx, we get a function in x only. So on doing this, we know that by integrating df all over f, we have f, which is a function in x only. Sorry, we have ln f, which is a function in x only, which is equal to the integral of rx with respect to x. So this means we have f of x to be equal to e raised to the power of integral of r of x dx. And this is our integrating factor when f is a function of x only. So this concludes the first case study in getting the integrating factor that is necessary to convert an inexact differential equation to an exact differential equation. In the next video, we are going to be taking a look at the second case study, that is when f is a function of y only. Then after evaluating the second case study, we are going to make a summary of the results that we've obtained, after which we now solve some examples to further aid our understanding of these concepts. Thank you for watching this video.